Hello, I'm Tom Bewley. This is the longer of two video presentations about our paper, Modelling Agent Policies with Interpretable Imitation Learning. So this is a paper by myself, Jonathan Lawry and Arthur Richards at the University of Bristol. And it's also supported by TAILORs who are partially funding my PhD. The particular problem we're interested in here is the modelling of black box autonomous agents for the purposes of trying to interpret their behaviour, generally build understanding, which is kind of part of the general effort in explainable AI. So we have here a representation of a black box agent, which is characterized by the fact that we can view its inputs and its outputs, but we are not able to see anything directly in terms of its internal representations. So this black box agent we assume is embedded in some kind of environment. Typically we use a Markov decision process formulation. So this environment has a state S at any given time. The black box agent ingests this state and uses it to produce an action A. That action then goes on to influence the state for the next time step. So our goal here in this modelling exercise is to basically produce a parallel model that also is able to observe the environmental state and produce an action A prime. And really the goal of this is to match the model's action A prime to the true action produced by the agent A as closely as possible. And any loss between these two outputs we can use to feedback on the model itself, update its parameters, and basically improve the predictions. So far this is typical vanilla imitation learning. So our particular aim here is interpretability. So to that end, we want to impose a certain structure on our model that allows us to understand it and analyze it, and hopefully through that process gain some understanding of the black box agent itself. So the particular structure that we're imposing here is to decompose the model into two stages. The first of these stages, which is represented by phi, this is a feature generator. So it observes the environmental state and generates a set of numerical features which we hope are individually interpretable in their own right. So you can understand where those features come from and what they individually represent. And the second stage of the model is an actual policy function, pi. So pi takes our interpretable features and maps them into an action prediction. And the mechanism by which it does this mapping, we hope, is also an interpretable process. So in our particular implementation, this is a set of discrete rules as represented by a decision tree. So that is our two-stage decomposition. So the aim here is to have interpretable features and an interpretable function of those features that mimics the black box agent as closely as possible. And this little graphic is basically here to show that the entire structure of the model is transparent and open to human scrutiny. This is the objective of this process in kind of formulaic terms. We're trying to minimize the loss L between the output of the model, which is this compound function of the features generated from the state, and the policy function of those features. So we want to minimize the loss between that and the true output, the action produced by the agent, subject to this constraint really that both phi and pi, or the spaces in which we're searching for pi and phi, are interpretable. And our hypothesis really is that if we can minimize this loss subject to these constraints, then we have a model that can facilitate some kind of understanding of the target agent's policy. So this bears some resemblance to a kind of common adage, and we've got a quote here from Feynman to that effect, that basically by being able to replicate the input-output behavior of a system of interest using a model of our own, then we're getting towards some kind of functional practical understanding. Let's go into a bit more detail about these two stages of our model, which we hope are individually interpretable. So the first one, this feature generator, what this does is generate vectors of real valued features from the state, and it does this by recursively applying a set of elementary operations to that state in a kind of recursive manner. So you can construct, in theory, arbitrarily complicated features, but if we understand all of these different operators individually, then they're imbued with a kind of semantic content, and we can see how they're composed. I'll give an example of exactly what that means in our experimental context, which will hopefully make it a little bit clearer. And pi, so the space of actual policy functions, This is the class of binary axis-aligned decision trees over these particular interpretable features. So we're inducing or creating these decision trees using the standard CART algorithm. Now to actually introduce the environment in which we've deployed and evaluated our approach. So it's a traffic network environment, which we've created ourselves. So each vehicle in this network, and you can see some examples of these networks in the figure. Each vehicle here is controlled by an individual policy, and it's a common policy shared by every single vehicle in the network, and that policy effectively has to choose between 5 different acceleration levels, from a hard deceleration through neutral maintaining constant speed to a hard acceleration. And basically their aim here is to navigate around the track without crashing into each other, either with the cars in front or also, most crucially, at the junctions, the various junctions in the network. So we've got 2 different control policies, individual control policies, that we're looking at as our target agents. The first one is a simple set of rules, which is actually directly equivalent to a decision tree itself with 39 leaf nodes. This is called pi-f because, in theory, we can fully imitate it using our approach. We could create a perfect model of this system because it is a decision tree, and the features on which it operates are exactly examples of the kinds of features that we can generate using our recursive operators. The second controller is a little bit more complicated, so it incorporates various different proportional feedback controllers. This involves continuous control functions rather than discrete rules, and this means that even in theory, it can only ever be kind of imperfectly imitated or partially imitated with a decision tree of finite size. So we've called this pi-p to show that even in the best case, we could only get a partial model of this system. And we should make it clear that despite the fact that we have hand-created these control policies, they are effectively black boxes from the perspective of our modelling process. We can't see anything about their internal mechanism. All we see is the input-output data, and our aim really is to recover this structure as much as possible. Now I'll talk about this feature generator. This involves basically domain knowledge in order to define a set of operators that make sense in this particular context. So in the context of a traffic network, we've got 8 different operations here that we allow the system to use. I won't describe them all in depth, but they do things like query the positions and speeds of different agents in the network and find differences between them, so find relative speeds between different vehicles, distances from vehicles to junctions, so find out how far a vehicle is away from a certain junction, and also find out which vehicle is in front of any other particular one. And through this process, you can kind of skip through the network and take any kind of useful measurement, intuitive measurement that you might want to of the state of the system. So some examples of features that would be generated by taking these features and applying them in a kind of recursive manner. We've got a few of them here. The first one, which we've highlighted, you can read it left to right. It basically finds the separation between the position of the junction in front of vehicle X and the position of vehicle X itself. So in natural language, that's basically how far is this vehicle away from the junction. The second example here, we subtract the speed of the agent or vehicle in front of vehicle X and the speed of vehicle X itself. So this is basically the relative speed to the vehicle in front. So both of these things are very intuitive features to kind of use in this environment. And there's a bunch of other many more complicated features that can be generated through this process. And in total, in fact, this particular set of operations ultimately generates 308 unique features. It can generate a lot more, but many of them are redundant and ultimately reduce down to the same thing. So we've got 308 features to kind of search from here. And the difficulty is that only 6 of them are actually required to perfectly imitate the first of our target policies. For the second target policy, the features don't exactly map onto the representations it uses, but you would expect far fewer than the full 308 features to actually be necessary. So we've kind of got a needle in a haystack problem, or a feature selection problem, or it's also called representation learning, about finding which features are going to be useful for creating this model of the system. So now the actual process that we use to create this model. So first off, we observe the vehicles driving around in the environment. That allows us to collect a set of environmental states and their actions, so accelerations. And we do this in a set of 5 different road topologies, which were in the figure a couple of slides back. And we have 11 different vehicles on the road throughout this process. So for each of these vehicles, we're able to create a vector of these 308 observation features. So it's things like how far is this vehicle away from the junction in front, or the relative speed to the vehicle in front, which we saw as an example before. And by concatenating all the observations from all the different vehicles, so we treat them all equally, we get this large data set of over 100,000 samples, with each sample having 308 features, so it's a large feature vector. And we feed this whole data set into the CART decision tree algorithm. And that CART algorithm tries to grow a decision tree that tries to predict the agent's actions, accelerations as effectively as possible. And we actually grow this tree until it obtains 100% predictive accuracy on the training set, but we would expect this to be massively overfit to the training set. So the next thing we do is we use a pruning technique called minimal cost complexity pruning, and that reduces the tree size back again while trying to preserve the accuracy as far as possible. And we use a separate validation set to select several of these pruned trees that will give a good balance between the size of the tree and the predictive performance. You can see here how we selected a selection of pruned trees for each of the 2 target policies on the left and the right. So the graphs on the top row are the predictive accuracy on our validation set, so not the training set. As you prune back the trees, the validation accuracy effectively doesn't decrease at all because there's a lot of overfitting in the unpruned tree. And in fact, the validation accuracy slightly increases as you go right to left. But then beyond a certain size of the tree, it starts to drop off again as you're losing some fidelity. The graphs on the bottom row basically show how many of the 308 features are actually used at some point in the tree. And this also diminishes, predictably, as you reduce the size of the tree. For the first of these policies, it's interesting how linear that seems to be in the size of the tree. The orange markers show how we've selected a selection of different trees throughout this pruning process. We've not followed a particular rigorous approach to do this. We just wanted to find a good spread of trees throughout the pruning sequence that would give a variety of different tree sizes and a variety of different predictive accuracy levels. This ranges from level 0, which are the original unpruned trees, all the way down to level 5, which are trees with something like 20 different leaf nodes, so that's an awful lot smaller than the original tree. Now for some actual results. So the metric that we're interested in here, or the first metric, is the predictive accuracy on a third data set, which is a test set. So this has been entirely held out in the inference process. And this is how well each of the trees of the different pruning levels can predict the agent's actions on each of the 5 different network topologies. So each column here is a network topology. The rightmost column is the mean value of that statistic. And each row is a pruning level of the tree. We've also got a selection of baseline models, which I'll talk about and introduce as I go on. I won't discuss every aspect of these results, there's quite a lot going on here, but I'll talk about some key takeaways. So first thing to note is that for both of the 2 policies, pi-f and pi-p, the mean predictive accuracy across all the different topologies exceeds 90% for even the smallest of these prune levels, and actually 95% for the second smallest of them. For pi-p, which is the more complicated controller that we can only hope to ever partially model, for this one, the maximum accuracy that we get to is around 97.5%. Because this policy isn't itself a decision tree, we might not expect to actually be able to get higher than that. One of our baselines involves supplying the 6 features used by the fully imitable controller, the simpler controller, actually providing them up front. So you remove the representation learning requirement. You would expect this to simplify the problem, and it does yield somewhat better accuracy than giving all 308 features to select from. But it is actually interesting and kind of promising that down to level 2 of the pruning process, the performance actually differs by less than 0.25% for both of the different target controllers. So we also have another baseline that involves giving a set of naive features which involve measuring Euclidean distances to vehicles and doesn't factor in the topology or the position of junctions. We'd expect this to be an inferior representation of the system, so you wouldn't be able to capture every aspect of the behaviour properly. And the results match that expectation. The accuracy levels for this baseline are much lower, so it demonstrates the importance of choosing the correct features when you're trying to perform accurate imitation. Another baseline that we used involved training on just one of the 5 topologies. So using topology D, which you can see is a relatively complicated network with quite a few different junctions, this actually generalises pretty well to the other topologies. But if you train only on topology A, which is this figure of 8 shape with just a single junction, we can't really generalise at all. This suggests that in the latter case, we've basically seen insufficient variety of the arrangements of the various vehicles to properly disambiguate between all of the hundreds of features and really nail down the decision rules that are being applied by the target controllers. For our second metric of evaluation, we actually take the decision tree models and use them as control policies in their own right in the environment. And a good metric for assessing the performance of these controllers is just how long the system is able to run before a failure occurs within the system. So we define this as either a crash or a stall in which the entire traffic flow grinds to a halt. We found that this happens occasionally and is also a undesirable outcome. So we measure this over 100 different episodes of 1,000 time steps, and we basically calculate how frequently one of these different failures occurs. A value of 100,000 would actually indicate that no failures whatsoever occurred during this testing process. We can see that the results broadly correlate with the accuracy performance, but we see a much more marked distinction between pi-f, the simpler controller which in theory can be modelled perfectly, and pi-p, the more complicated one. And we also see more variation between the various test topologies. But despite this, we can see that there is quite minimal degradation in the actual on-policy performance of the trees, all the way down to level 4, with a constant average of around 1 or 2 of these different failures for the first controller, and around 3 or 4 failures for the second controller. And in fact, it appears that the intermediate pruning levels, so not level 0, the largest tree, actually fail less often than the larger trees. These results don't show immediately why this is the case, but it might be that having fewer leaves in the tree yield less frequent changes of acceleration as the policies are deployed, and actually produces smoother driving performance. Looking down at the various baselines, we can see that providing the 6 correct features up front actually doesn't really confer any benefit over giving all 308 features to select from when we compare it against the highest performing prune level, which is level 3. But again, using the set of naive features and also doing single topology training on topology A, these trees are extremely poor when used as controllers. A final thing to look at, this wasn't actually included in the paper itself, but we can easily look at the internal structure of the decision trees that we've learned and try to compare them to the target controllers to see how good a model they actually are. So we look in here just at the smallest of the prune levels for pi-f, the simpler first controller, which is itself represented as a decision tree. So we can try to compare how similar this tree is to the true ground truth one. So this pruned tree has 20 leaves. We've seen it obtains over 90% predictive accuracy, and it achieves a mean of around 12,000 time steps between each failure that occurs when it's deployed as an actual policy. This tree uses 11 out of the 308 original features, which is obviously only a very small subset. And within this set of 11 features, we actually have all 6 of the true features used by the target controller, which is a fantastic result. The learning process, which we should remember is based purely on observational data, has done a pretty good job of recovering some of the internal structure of the target policy. And in terms of the decision rules themselves, the thresholds at which the decision tree is actually making decisions actually really closely match the true decision thresholds inside the rule-based controller itself. There are a couple of other features, though, that have been used by this tree. 2 of them actually are just the negative of one of the real features, or 2 of the different features subtracted from each other, so they're not truly spurious, they're just slightly different representations of the correct features. But there are 3 features that this tree uses which we could describe as genuinely spurious, or we know that they're not actually used by the original controller. And I've highlighted the 3 decision nodes within this tree that use features that we know are not present in the true model. So really the rest of the structure of this tree does reflect the true internal structure of our target model. The decision rules may be applied in a slightly different order, but they actually are reflective of the real decision-making process inside the agent. I've also included a quick graph here of the feature importance statistic for the 11 features used in the tree. This is something that could be quite easily computed for a decision tree, and we can see that 2 of the features are used quite heavily, and these are both correct features that are actually present in the original model, and the 3 spurious features aren't assigned a huge amount of the overall importance weight. So finally, just a summary and a discussion of the main findings of our investigation. So we've explored this recursive method of constructing interpretable features using a set of hand-picked operators. And we think this is potentially a promising method of delivering interpretable representations without actually assuming the exact set of features to be used up front. It creates a space of interpretable possible features without us having to commit exactly to which ones are going to be best. As expected, the results also show that we do a better job of imitating the first target policy, which is itself implemented as a decision tree. So you do better when you match the model class of the target policy with the model itself, which is something that makes sense. But it's obviously difficult in general in a black box context where we might not know anything about the internal structure of the target policy to know exactly what model class will be best for attaining high accuracy. We also see how the 2 metrics of predictive accuracy or fidelity and the on-policy performance in terms of the mean time between failure, they're correlated, but they aren't exactly the same metric. We see in general the performance or failure metric varies a lot more wildly, so small changes in the accuracy could actually yield very large differences in the ability of the decision tree models to actually perform well if they're used as policies in their own right. This problem is likely to be related to the problem of covariate shift in imitation learning, which basically says that any small deviation in the predictions on a single time step basis can cause a quadratic accumulation of error over time as a system is deployed in a dynamic context. And finally, just a conclusion about our overall modelling approach. So our approach of using the CART algorithm followed by the minimal cost complexity pruning does seem to be an effective method of recovering a small set of correct features from a large bank of candidates. But despite this, some spurious features do seem to remain in the decision trees that we learn. These spurious features are useful from a predictive perspective, despite the fact that they aren't actually causal of the agent's true behaviour. This is effectively a problem of causal confusion. And it might be that we need some kind of active learning scheme where we intervene with the system during its operation in order to disambiguate between correlative relationships, such as those between the spurious features in the action, and true causal relationships, which would exist between the features actually used by the agent. This is a really interesting issue and definitely something that we're hoping to pursue in ongoing work. So that brings me to the end of this presentation. If you're interested in learning a bit more about this work or just generally getting in touch, I've put my email address there as the correspondence for this work. Thank you very much for watching.